Okay, hello everybody. I'm Ilya, and today we're going to be talking about emulating IoT firmware and malware with Docker and QEMU. I'm calling this new tricks for old techniques because this is the same stuff that we've been doing a long time to emulate devices. It's just new tricks to do it in ways that are a bit easier to work with. I'm going to give a bit of background on why I started doing this research and where everything came from. Originally, we were intending to do this to create a CTF that would be all IoT target devices, and each team competing in this starts off with a C2 node and a single infected bot, which they then use to scan networks and attack other targets. At the end of the 24-hour period, the team with most bots wins, and the end result of this attempt at building the CTF was a working proof of concept for putting together a IoT botnet lab. The CTF itself is still unfinished, but the research here that I think is valuable to share is just how all of this was put together, because it has more applications beyond just building a CTF for a game event. And yeah, one of the major technical challenges that we had established from the outset in building this project was any malicious traffic stays within the subnet that the botnet lab is running in. So we don't want to be accidentally sending out malicious traffic from our botnet lab to the internet at large. Here's a quick roadmap for how we're going to break down this talk. The first section is a quick introduction to basic concepts, user space emulation, multi-arc containers. The second section is the real meat of it, where we're going to go through some case studies to demonstrate how this proof of concepts works, to demonstrate these techniques. We'll discuss some of the applications this has to vulnerability research, exploit development, other security-related disciplines. We're going to discuss the advantages and limitations, and also some ideas for further work and research and to continue from where I've gotten things so far. The purpose and motivation for this is basically that Docker makes it really easy to share appliances as container images. Basically, I can just, if there is a device that I want to emulate and somebody else has already built one, I can just Docker pull that thing, Docker start, and give it whatever flags it needs, and it comes up and running. So one person does the work to build an image of some vulnerable device, publishes it on the Docker hub, and then anybody who wants to research it can just Docker pull that thing and it'll run on their machine. There's no need to have like KVM and QEMU or doing any of the old-fashioned kind of techniques that is required to set up a working emulation environment. The IoT security is also notoriously poor. So one of the main things that we want to emphasize here is being able to research malware and also research firmware, any kind of software really that is running on non-x86 hardware. We want to be able to make it more accessible for people to do research on these things and to improve the state of security, and also to sort of work against the fact that attackers have a lot of advantages in this domain, because as we all know, a lot of these vendors don't even think about their security. Even if they did, the users aren't going to update the firmware. So yeah, this is a domain where a lot more research needs to be happening, and anything that can facilitate it, I think, is worthwhile to look into and to share. So let's talk about containers real quick. They're often described as being like lightweight VMs, but it's important to understand that they're not actually virtualizing anything. They're sharing a kernel with the host operating system, and a container is really more just like a CH root that has some extra restrictions imposed on it due to Linux kernel features like namespaces and C groups. So a container image is built from a Docker file. The Docker files just have all the instructions that are executed by Docker in order to build the image of whatever application it is that you're trying to bundle. Essentially, this is just like a tarball containing a snapshot of the root file system, and there's multiple layers on top of it. So you can easily extend and customize any Docker image that you find on the web. And here's just a quick illustration that shows how Docker images look. So like you have a Debian one, and then on top of that you've installed Java, and then on top of that you've installed Tomcat. So this is what it is meant by layering the things. The base image can be whatever you want: Alpine Linux, Ubuntu Linux, Debian Linux. There's all kinds of options you have out there for base images, and then you can put whatever software you want on top of it. The important thing to see here is also it's all sharing the host kernel. So this is the typical usage of a Docker image, very basic stuff. I'm just including this in case some people are not familiar with Docker or haven't really worked with it in the past. This first example is just a standard invocation of a Docker container. So I'm just running bash in that container, showing the Debian version, voila. And then this is a sneak peek at what a multi-arch container looks like. So you can see when I run the command uname-m within that container, it says it's a MIPS machine, but my workstation is in fact a x86 64 machine. So what we see here is it is in fact possible to make a container think it's running on a hardware that it actually isn't. And it is because of QEMU that this is possible. Most of you have probably worked with QEMU before. Most likely, though, you've worked with QEMU in what is called the full system emulation mode. This is usually how it works also when you're running QEMU alongside a kernel hypervisor like KVM. And you're typically managing QEMU instances through something like libvirt or virt manager, which is like the graphical front end for it. So these are all familiar tools that have been in our toolbox for a really long time. In the full system emulation mode, we are booting the entire operating system, which has its own kernel, RAM disk, init file system, everything. It goes through the exact same process as if it was booting a real hardware device effectively. However, there's another mode that QEMU supports, which is the user space emulation. And this is useful for transparently executing cross-compiled binaries on your workstation. And for our purposes, it is this QEMU user space emulation that we're going to be interested in. So what is this QEMU in user space? This works by basically doing just-in-time translation of emulating the target CPU architecture by it translates the machine instructions. So if it has some MIPS instruction, QEMU knows how to translate that into x86. If there's some MIPS syscall being executed, it knows how to translate that syscall into a native syscall on the host that it's running on. So there's no virtualization happening here. It is just like JIT translating the syscalls and machine instructions. It is important to note that there are many IOCTLs that don't work in user mode, and there are also some system calls that don't work. Usually these are if you run into situations where some device that you're trying to emulate in QEMU user mode doesn't work for one of those reasons. Usually it is pretty easy to patch that in QEMU. It is just new IOCTLs and system calls are being introduced to Linux kernel all the time, and the QEMU maintainers sort of lag behind that a little bit. And it's also important to note, and we'll discuss this a bit more later on, that the host kernel is, all of the system calls are being passed through the host kernel. We're not emulating a full system. There's no virtual kernel working here. And this has some ramifications if you're doing exploit development testing, for example. The interesting question is, how does the operating system know which QEMU interpreter to use for a given binary when it is doing this transparent user mode execution? And the answer lies in the, I'm going to pronounce this as bin format MISC. Maybe I'm butchering it. Who knows? Anyway, this is a file that lives under the procsysfs hierarchy. And so when the operating system is executing a program and it has this bin bin format MIPS table populated. It takes a look at the ELF section header in the binary it's trying to execute, checks the magic number. If that magic number corresponds to one of the entries in this table, then it will use the corresponding interpreter to execute the binary rather than just trying to execute it natively. So you can see here the QEMU MIPS register. It's enabled. The interpreter is user bin QEMU MIPS static, and there's flags, offset stuff all set there. The magic number is the magic number for MIPS executables. So now we're ready to talk about the multi-architecture containers. This is basically a combination of QEMU and this QEMU user mode and Docker. The first thing to make sure of is QEMU's got to be installed on your host system. This is accomplished by the first shell command up here. That'll install the packages you need. If you're not on a Debian-based system, then I'm sure that translates pretty readily into a Yum or whatever package manager you prefer. The multi-arch image repository on Docker Hub, it provides a script that will populate your bin format MIPS directory with all of the necessary entries for setting up the emulators. So this is kind of weird because it is a container that you're executing, but you're putting it in privileged mode, which allows it the ability to do stuff on the host that it normally is not allowed to do. In this case, it is writing entries into proc sys fs bin format MISC. But this is a very easy way to set up the host machine for running multi-arch images. And we can see in this last step that indeed it does work. You just do the Docker run on an ARM 64 v8 image, and you have the uname.shim. Indeed, it thinks that it is running on an ARM machine. There's a lot of available base images from the repository here. So you can see that there's Fedora, CentOS, Ubuntu, Debian as the main ones. There's BusyBox and just even the smaller one that's like bin true for a variety of architectures. So whatever your preference is, there is a base image for doing work on in Docker on a architecture that is not x86, and you can see the various architectures that they support here. So why is this useful for IoT security research? Well, I mean, first we can just execute cross-compiled binaries on on our workstations without any overhead. This is useful in a variety of scenarios, and that's not even limited to IoT research or security research. That's just useful for anybody that works on multi-architecture software. Another thing this allows us to do is debugging cross-compiled binaries without setting up a whole CH root or configuring a virtual machine for it. You can also do this for rapid prototyping of shell code or various payloads that you want to make sure are going to execute on a particular revision of a target CPU, or maybe you've ported some shell code from ARM to MIPS, and you want to make sure that it actually works. Then you have a very easy, rapid testing cycle right there, easy to use. We can also set up honeypots to get samples of malware that's targeting non-x86 hosts out there in the wild. So just a lot of imaginative use cases you can feasibly come up with for this. I've listed only a few here. So now we get to the real meat of this, which is emulating IoT firmware in Docker. The first challenge with emulating firmware is oftentimes getting the firmware. When you're lucky, or if it's a particularly well-known device, the firmware is pretty often directly available on the vendor's website. And a lot of vendors will even keep up the obsolete firmware versions that have known vulnerabilities in them, which is really sweet for the thing that we're trying to do here. There's also a scraper module that is built into Firmidine, which can fetch a ton of firmware images. Just like you let that thing run overnight, and you've got tons and tons of gigabytes of some of them useful firmware images. And basically, if you run out of luck searching the web for the firmware you're interested in, then you have to get creative. Maybe like you need to Wireshark and DD and intercept the actual firmware being updated from a physical device. Or there's a lot of techniques that I'm not going to obviously discuss here, but you have to get creative if you can't just find the firmware easily on the device or from the vendor's website. In our case study, we're going to be looking at two specific devices, the Netgear WNAP320 at the version 2.0.3, and the D-Link DUR 866L, and there's a long version string. So yeah, these I just got from the vendor's websites. And Firmidine is the tool that I use for extracting the root file system out of the binary blob that I downloaded from the firmware vendor website. Firmidine is awesome, and you can use it to set up a full system emulation QEMU environment that has all the peripherals. It infers the network setup. It does a lot of the tedious work for doing the whole QEMU full system emulation setup, but we don't want to do this. That's not our goal here for today. All we want to do is extract the root FS and then put it in a Docker image and let Docker do the execution. So this is a screenshot from extracting the root FS on that Netgear one. This is the top highlighted part here is the command I ran inside the Firmidine container to extract the squash FS out of it. And then you can see in the second highlighted part down here, I get a ELF. I guess it doesn't say that that's an ELF. But I get the root file system out of here. And I pass flags of don't extract the kernel or anything like that because we don't need it. We're going to be running this in Docker, and Docker, of course, does not allow us to use our own kernel. And then now that we have this firmware.tar.gz that was extracted from Firmidine, we can start writing the Docker file to create an image for this device. And I've just pasted the Docker file right here into this slide. The first line is just saying I'm going to refer to this multi-arch Debian dev bootstrap MIPS buster slim as QEMU. You can think of this as like a Python import statement, like import JSON as JSON or something. And then the actual build steps happen in the next line. So we start from scratch, which is a completely empty Docker image. There's no content in the scratch base image. You could, for example, throw a statically compiled hello world.c program in there and it'll echo hello world.c, but only if it's statically compiled. So this clarifies what does from scratch mean. It means absolutely nothing, because we don't want to be building this off of an actual Debian system or off of a CentOS system or even BusyBox, because we want only the files that we got from the vendor's firmware to go in there and nothing else, except for the QEMU MIPS static interpreter, which is on the next to last line. So we copy from the QEMU Debian image just the QEMU MIPS interpreter and throw that into the user bin. And then we say like the entry point, whenever you run a command in this system, is going to be passed through the QEMU MIPS static BusyBox interpreter. And so this Docker file is what I use to build images for all of the different routers I've emulated so far. The only thing that changes between any two of them is the contents of the firmware.tar.gz. And here's an example of the output from building the container. You can see how it runs through those steps and then produces a target router Netgear WNAP320 latest. And so that's something I could, for example, Docker push to the Docker Hub, and then anybody else who wants to play around with this router would be able to pull it. Excuse me. If you are playing along at home and you end up running into weird errors about can't exec BusyBox, there's a bug or something in the registration script that sets up. It will install both QEMU MIPS and QEMU MIPS N32 and also the N32EL. These have the same magic number as regular MIPS, and the computer will get confused basically if both of these are active at the same time. So you can just quickly disable those by echoing -1 into their respective bin format bin format table entries. So now we've built some Docker images. We have containers. We can explore the shell a little bit. Here's a screenshot of just poking around a little bit inside that Netgear router. You can see there's just what's in the root file system, pretty standard looking stuff. What's inside of the bin directory is, again, pretty standard stuff, nothing too surprising there. There is this weird thing I found where there's an admin user that's not root, and it has its own weird CLI and home directory. And inside of that place, if you look around, there's the firmware upgrade binary, some sort of password binary, restore factory default binary, a lot of stuff to investigate there. And at the very bottom, you'll see here what init scripts are there in the etc init.d directory. If you run the etc init.d/rc5 or RCS, sorry, that will run through all of these init scripts. And what ends up happening if you execute that init process, you get all the system processes coming up. So you can see here, as expected, everything is prefixed with QEMU MIPS static. This would obviously not be the case on the real machine, but the light PPD service is running, Dropbear is running, NTP client is running. So everything is up and running, and you also get the web interface that is being served over light PPD. And yeah, you can do pretty much anything you would as if it was a normal router. There are some limitations, obviously, with how this is set up. The networking config is not the same as it would be on the router. There's obviously no wireless interface device that I've put or attached to here, although we could probably fake quite a lot of that. But you do get a working web interface out of it. And this is in the D-Link router, just taking a look around that. It has, under SBIN, again, some pretty common stuff, nothing too surprising. What was the interesting thing here? It has a lot of it has a ton of PHP files in Etsy services, and that's, like, I'm gonna just guess, a gold mine if you're a vulnerability hunter. And also the Etsy config directory has some weird stuff in it. There's all these, like, looks to me as if they are remnants from a dev machine or something that is used to do builds or sign images or something. Anyway, a lot of really weird stuff. If you actually are able to get a shell on these things and go looking around, you can find a lot of weird stuff. So that brings us to the next point of IoT malware emulating in Docker. Because now that we have some routers to attack, let's see what we can do to them. So this section of the talk is mostly going to be a case study of the Mirai botnet. I assume everybody is familiar, but I'm just going to cover this real quick. It targets primarily Linux-based commodity routers and IoT devices. The source code was released on hack forums in October 2016, a few months after the botnet was discovered by researchers. Since this is a fully open source and freely available piece of malware that's now in the public domain, and since so many different variants of it have emerged as different DDoS gangs, I guess, have made their own variants and modifications, there's a lot of proliferation of the Mirai botnet. So it's out there. It's attacking stuff that is running mostly on MIPS or ARM architectures. We have access to the source code. It's pretty well understood by researchers at this point, and it's a good candidate for our case study of building a botnet lab in a controlled and safe way. So this is a quote from the Hack Forums post where the alleged author is bragging about how many bots per day that they're able to pull with this botnet, and they're claiming that they get 380K bots from Telnet alone. So just by brute forcing things on Telnet with default creds, this person is getting a ton of bots just with pretty much no effort. And the reason I include this is because it speaks to the real threat that this poses. Like, that is an insane number of bots to just be getting for very little work. And so, like, threat actors now are basically anybody who can spin up a botnet. And like, the biggest denial of service attacks that we've seen in recent years have come from these silly IoT botnets that doesn't require much sophistication to set up or operate, but they can do a lot of very real damage. So I think this quote says quite a lot about the state of IoT security and the real threat that is posed by these botnets to internet infrastructure overall. So the Mirai botnet architecture is divided up into basically two components. There's the C2, which is written in Go, and then there are the bots, which is, or the bot is written in C, and then it's cross-compiled to a bunch of different architectures. And those cross-compiled binaries end up going into a web server, which runs on the C2. Whenever a bot discovers a new target to attack, it will then like install itself from that C2's web server or TFTP server or whatever. It puts those binaries into a bunch of paths, and they're pretty easy to find if you go looking for them. Anyway, this code base is pretty insane. It has all kinds of silly stuff like this anti-GDB entry function that really seems to do absolutely nothing. There's so many gems of madness in this code base that it's been a lot of fun and jokes working on it. It also takes quite a bit of guesswork to figure out exactly how it was meant to be compiled and put together. And if you go and look on like any of these like SCID hack forum stuff, it is mostly people asking how to use GCC effectively. But anyway, through a process of trial and error, I was able to get a working containerized build pipeline for this for a customized Mirai variant, because there are some changes that I had to make, which I'll show you a few of them here. So this is the source tree on the left-hand side. As you can see, it is basically as I had described. The makefile.in, and that compile bot script are things that I wrote and added to it to sort of save my own sanity. And in the right-hand side, you'll see here some of my C programs that or some of my changes to their bot scanners C program to neuter that activity. So and you'll see what this means in the next section. Basically, this get random IP function, which was already built in there, I just completely rewrote the implementation of it, will get an actual random IP address that is from, they have a set of subnet masks that they exclude. So like anything that's in the DoD or ARPA networks, they will exclude from the get random IP function. So there's like a few subnets that they, I guess, don't want to be doing any attacks against out of fear of detection or repercussions or whatever. I'm not sure why, but they have this whole enumerated list of networks they don't want to mess with. That's fine. They get a random IP, it's an IP address on the internet, and then the bot will just start automatically attacking it. And so the first time I got this to actually run and execute on my container, I was so excited, and then like immediately I started seeing, oh my god, it's attacking IP addresses all over the internet. So immediately I shut it down and then started getting to work on writing this modification. So yeah, you can see here the output of this now this up here is the bot running, and it's just getting random IPs that are on the 172.30/16 subnet. So this was a really important part of being able to make this a safe thing to run in a lab environment, because, like I said, biggest problem with doing this kind of stuff is you might accidentally start attacking things you don't mean to attack. I also had to make some changes so that it knows the IP address of my C2, because the C2 is running also in Docker, and it has a hard-coded IP of 172.30.11. So this is something that I had to change as well. Here's yet another gem of madness that I wanted to include just to give everybody a sense of how insane the botnet is. These are all of the username and password combinations that it shoved in as hard-coded things. It's just, and it goes on and on and on like this. I'm not even joking. So you can see kind of the skill level, and also you can imagine that these binaries are also have fairly predictable strings inside of them. They do all of these encoding things just to try and make it a bit harder to reverse engineer, but it's actually not that hard. Here's the Mirai interface, how it looks like, in case you've not ever had the pleasure of working inside of it. So the way you connect to it once it is set up is you telnet localhost on that on whatever port the C2 is configured to listen on. You put in the password and username, root, and I see, oh wow, I've already got a bot, because this is the bot I get for free in the CTF lab. That's about it. You can see all of the various options and flags you can set when you're using this to do a DDoS attack. Just put in all the C2 options here for the sake of making sure people know what it looks like. So building this Mirai image all takes place inside of Docker container. So there's no needs to have Golang stuff installed on your actual workstation. There's no need to install a bunch of cross-compiling stuff that you're going to end up breaking something else on your workstation. There's no need to like talk somebody else through how to set up a multi-arch build environment. If you've done it before, it's not the hardest thing in the world, but it's also not always easy, and it, much better to do it, I think, inside of the Docker container, especially since this is all going to be copying files into containers that we actually want to run for the lab. So I'll walk through here very quickly. We start with a just generic Debian stable slim image as our build base, install some core packages, then we install Golang stuff, add a user, so we're not doing this all as root, copy the assets, and I have also this cross-compile script that downloads cross-compilers inside of the container, and then it just like sets that to be executable, and then it runs the scripts to download all of the cross-compilers and put them into /op/cross-compile or whatever. Then the build base, it just copies the source files for Mirai into the build directory, and then it just runs the make build and make install command, and it's done. The C2 image then imports that base image, or like it references it the same way that we reference the other one earlier, just so that it can be referred to as Mirai build. We do the same thing, run apt-get update, set some stuff up. We make the directories for where we're going to copy the bots and the downloader, so that when the bot is able to do an infection on another machine, these are the directories where the bots and the downloader is actually going to be served from. Some of the stuff here is just for the Ansible setup that I use for the CTF lab. You can feel free to ignore that. And then we copy all the stuff from the Mirai build. So that's you can think of that as just like the build machine or the CI server. And then we copy all those artifacts into our Mirai C2 container itself. We also copy the database dump that is going to need to run on first load. And we make sure that we expose the appropriate ports. The first port is obviously SSH, and the second port is the C2. The bot image, very similar. So this one is a bot that is used for testing. It basically comes pre-infected with Mirai. So this goes through a very similar basic process. Mostly it is used for testing the testing that the bot connection works to the C2. And now we have all the components we need for like a minimal proof of concept. Here's the Mirai C2 container up at the top. You can see that I've got a bot connected, and it tells me the IP address of the bot. And from the second part of the output here, you can see the bot is indeed confirming that it was able to connect successfully to the C2 server. So nice. We have a minimal POC of a Mirai C2, a bot running on a MIPS Debian machine, and they're connecting and able to scan the rest of the network. So beautiful. Now we can put this all together with Docker Compose and bring up a full lab environment with just a single command. So you can see here, I run make start. That hits my Docker Compose file. The Docker Compose file defines all of the networking setup and any like volumes that need to be mounted, for example, SSH keys that get used for the Ansible, because I want to be able to control everything in this lab with Ansible. And you can see again, yep, everything is up and running once the Compose script runs. And we have a botnet in the box. That's pretty cool. So the limitations and advantages of these techniques are very important to mention. So the advantages are now we can easily explore the contents of like a wide variety of IoT devices, especially routers. They seem to be the easiest for some reason, with relatively low overhead. We can also do rapid prototyping of exploits against these machines and test out payloads on exotic CPU architectures. We have a lot of opportunities for automation because one of the main use cases for Docker is it makes a lot of things easier to automate, like CI and CD, automated testing, deployments, putting things into pipelines, even just like deploying stuff to Kubernetes. We have a lot of opportunities for more automation than we would have if it was just like sharing around the QCow images or something that work differently on different people's machines. So that's the most important point, I think. We can share these images, we can build on top of each other's images, and people are able to actually explore and study these IoT devices and also these samples of IoT malware. So yeah, the ultimate goal of this work is making IoT security research more accessible, more efficient, and reproducible. Now, the limitations and drawbacks. I mentioned earlier that there are a lot of IOCTLs and syscalls that are not emulated necessarily in the QEMU user mode. In most cases, again, these are things that just need a patch, and the only reason that they're not there is because nobody has asked for it yet. Another major sticking point is that a lot of these routers and IoT devices, they store important state information in their NVRAM. This is typically accessed through like a shared library interface, but the container doesn't have NVRAM, and we haven't set up any kind of like LD preload trick to make it think that it does. So any calls to read or write values to NVRAM are going to fail. And this has limited my ability to do the same thing with certain like Huawei model routers. Their init scripts, when it runs, seems to do a lot of NVRAM reads and writes. And when it isn't able to do those, it fails in hard to debug ways, actually. So some machines, this isn't such a big stopping point, but for other devices, this actually is a huge wrench in the machine. But there are workarounds that we can work on in the future. Another important thing to think about, especially if you're doing this for a CTF or if you're doing exploit developments and you're working on an exploit where part of the chain is going to be like privilege escalation through a kernel vulnerability, well, you're not going to get that because you are not running on the actual kernel that the target device is going to be on. The kernel that the router has is actually your host kernel. So this isn't necessarily useful for every conceivable kind of security research, but it is useful for quite a lot of stuff, and you can get a lot of information out of just checking the file system and seeing what's there. Oh yeah, and in the same light as the NVRAM stuff, there's a lot of guesswork involved with getting the routers to function fully as intended. So like they don't come with any developer docs, they don't come with a README or anything. You just have to kind of figure out, oh, that's the init script. That's the thing that I have to run to get everything coming up. Oh, this is the line I have to comment out to make it not fail on that NVRAM load. So there's a lot of guesswork. The nice thing about this whole system that I'm proposing is one person or one team basically figures out for a given device from guesswork what changes needs to be made, and then they put together an image, and that image will work for anybody else. So the cost of figuring out how to make a router emulate under Docker with QEMU is amortized as soon as one person or one team does it. So yeah, ideas for further research. There are some LD preload tricks that we could use to work around a lot of these NVRAM limitations. In fact, the Firmware with full system QEMU emulation, it does this for you automatically. There's also the NVRAM faker library on GitHub. So there are a few different approaches to working around these limitations on NVRAM. It is also possible, I think, at least with NVRAM faker, to put in a config file basically what values you want to be associated to what registers, and you could do a lot of other cool stuff playing around with that. Another thing that needs to be done for further research is I've confirmed that this works 100% for the routers that I've tested. I haven't had much success with IP cams or like smart toaster or anything like that. The firmware for some of those things are hard to get, and the ones that I have been able to get my hands on did not translate neatly into a firmware tarball that would work under this process. So more devices need to be researched for this kind of technique. Some other changes that would be cool to do is exposing a GDB server from the container images, so then you can attach a debugger to the running process inside the container and get a more full view of what a particular component of some router is doing, or what some piece of malware is doing. Dynamic analysis kind of stuff. I would also like to be able to use the bots to use DNS instead of having a hard-coded IP address, because that would make it a lot easier to set this up for a CTF specifically. More reliable firmware scrapers would be very good to have. Automating the rootfs, like just automating the whole process would be really cool too. So then, like, if we have a scraper that scans the internet for firmware images and pipes it into the like rootfs extractor scripts, and then that itself triggers a build of the image and a published Docker hub, then like we have a pretty nice system for fully automating build pipelines for IoT container images. And I think that would be really cool. So here's some references and further reading. There's a link to the GitHub repo with my proof of concepts. Quick note, I haven't actually uploaded it there, but I've just kept it in the slides as a placeholder because I plan on doing so in the very near future. I just need to clean up a few things. Here's the Docker multi-arch repository and Docker Hub page, Firmidine, a lot of really useful information in their README, and the archive of the original Mirai source that was posted to Hack Forums. If anybody wants to review that, it's a lot of fun. I want to also shout out to you, NetSpooky, for helping out with a lot of these ideas, sharing his annotated Mirai source with me, and just overall being an awesome person and encouraging me throughout the cycles of doing this work. A lot of people from Thug Crowd have contributed to this project in some way or another, so love you guys, thank you. And the hardware vendors who keep putting out their old firmware images, thank you for doing that, because otherwise I would have nothing to test with. So also thank you for listening, and to the organizers for putting this all together. It's a lot of work, so thank you everybody, happy hacking.
We think about IoT Village as a movement. These devices are being adopted so rapidly that security is not effectively being baked into the development and deployment of those solutions. That puts consumers at risk, that puts businesses at risk, that puts governments at risk. And what we're trying to do is to galvanize a community around solving that problem.
Every time somebody hears IoT, they immediately think, I don't want this in my house. But as time goes by, that choice of having something in your house or not is not really there.
You can walk in the village, you won't feel like you're asking a dumb question, and you'll still walk away learning something no matter what your skill level is or knowledge.
IoT Village provides an opportunity for people to experience security in a very tangible, very real way.
So what ends up happening is, I can kill Lisa right now. She's being smothered. She's flatlining, patient monitor's going nuts, she's dead. What's going on at the nurse's station? She's fine. What I'm doing right now is we are replaying recorded data of a healthy patient. So this patient monitor is something you'd see in every hospital room in America probably. The IoT Village seeks to raise awareness of IoT security. We want consumers to be able to make informed decisions, and we want manufacturers to improve their security.
So we put a lot of work into the security on the Bird 2, and we wanted to put it in front of the DEF CON community and see what people were able to do with it. We've learned stuff about our tech that we didn't previously know, and from my perspective, that's phenomenal because we have a really talented team internally, but when we can be educated by people external to the company, it's a big, big win.
We really want to show that we very much welcome the work that security researchers do, and even though we work in a world, the medical device world, that's not as accessible to the people that work in this space, we really value the input that researchers have. We want to show that we love for them to work with us on medical devices and what they can find in it.
Security is a mission-critical part of being a pioneer. And by participating in this, they're able to address some of the challenges that are introduced through innovation.
Building a contest to challenge hackers, at the world's biggest hacker conference, if these guys didn't know what they were doing, this room would be empty.
So IoT Village is awesome. Unfortunately, like a lot of hackers work in these small groups, they don't really share a lot of information because they kind of want to monetize or capitalize off of the information that they have. So being here in IoT Village gives us an opportunity to talk to a bunch of other hackers that we wouldn't normally talk to and share information and kind of like come together as one.
I think it is the best thing since sliced bread, personally. This year we're here at DEF CON helping run a hands-on lab, IoT Hacking 101. How do we get people involved with this? Because it might be intimidating, right? Walking up into a big CTF at a big conference. The idea is that we handhold them all the way through from the basics of firmware analysis right through to discovering a bug and popping a device or two.
I just connected over Netcat. There was nothing fancy, no authentication, anything like that. And this number here is your authentication token. It's a serial number on the device. That's what they're using for authentication. So what we're doing is that we're showing people how we find vulnerabilities in embedded devices. Specifically, I've been targeting NAS devices, and I've been showing how we find vulnerabilities, develop an exploit for it, and exploit it from the attacker's perspective.
IoT Village is the face of IoT security worldwide. They're probably the most preeminent brand when it comes to dealing with IoT security. We have expertise, they have expertise, and we feel that it's more than just a sponsorship, it's more of a partnership in which we share stuff with each other. The visibility that you get from all of these conferences is an amazing thing.
It's only going to get more and more relevant, and the devices are only going to get more and more prevalent. And so I think it's just a great interactive, hands-on experience for people to come and get immersed.
We know that these security challenges that are inherent within connected devices, they're not going away on their own. We're able to make these challenges come alive, to become real, to be tangible. And when we do that, we enable people to participate in being part of the solution.